Continuing on, looking at drawing Lewis structures, we're going to focus on polyatomics. So all of these ideas about Lewis structures and how to describe molecules is also going to be equally applicable to polyatomic ions. Those, remember, are close atoms bound together by covalent bonds that overall are charged. The only difference comes in when we start to determine the total number of valence electrons. And it's going to depend on the charge of the ion we're looking at. If we have an anion, we add electrons, right? Because anions have overall more negative charge. They have an extra electron. So in this case, hydroxide was negative. And so overall, we then need to add. That means there's one extra electron. If we were dealing with a cation, something that was positively charged, we would subtract an electron because there's been one overall electron lost from that molecule. When we're actually drawing the Lewis structures, we can see that we have these brackets. And what those brackets imply is basically we have the brackets around the molecule with the charge up at the top. And what that is showing is that that negative charge is on the whole molecule. This is a polyatomic ion. The charge is spread out over many ions. It's not just on one. And so these ideas of looking at charges and how it affects everything applies for any polyatomic ion. If we're looking at, say, cations right here, +1, so that means we subtract 1, okay, because it's a +1 charge. Carbonate, CO3, 2-. In this case, it's a 2- charge, so we know anion means we're going to add electrons, and we add a number equal to the total size of the charge. So in this case, we add the 2 electrons in the case of carbonate. So whenever we're dealing with polyatomic ions, we can use the same approach we already talked about of how to come up with the Lewis structure. We just need to modify when we're figuring out the total electrons, add in the effect of that total charge. When we're drawing it, we can just draw those brackets. Sometimes people do or don't use brackets because you don't need the brackets to determine its charge because you can figure out how many electrons are in there. But that is something we can do when we're trying to describe polyatomic ions. All right, so let's do another example. Let's do a bunch of them. Nitrate, NO3-. So one thing is, start off, what are the valence electrons? So there's 1 nitrogen, that's 5 electrons, 3 oxygens, that's 3 times 6. Each of them brings in 6 valence electrons. Because it's an anion, the charge is -1. That means there is 1 extra electron. So I'm going to add in that single electron. That gives me a total of 24 electrons. So the first step is draw out the skeleton. Just get something made. Again, the central atom is going to be the first atom. That's the nitrogen here. So I draw N, and then I just draw single lines out to the O's. Okay, so I have that. They're all out onto the O's. Everything looks good so far. Okay, so I need to account for that. There were 6 total electrons 24 total electrons I started with. I just assigned 6 electrons in those bonds because there's 3 of them. So there are 18 electrons left to assign. Next step is to add in lone pairs because each oxygen only has 2 bonds or a single bond as it stands. They all need 6 electrons to fill their valence. They're all looking good now. So everything looks good. And next step is to subtract out those. So that was 3 atoms, each with 6, 18 total electrons in those lone pairs. So there are no electrons left. And so if I take a look, the outer atoms, all those oxygens are good. By definition, I just gave them octets. But the nitrogen only has 6 electrons here. So that's not good. Something needs to happen there. And so what I can end up doing is I can take one of those lone pairs on the outer atom and turn it into a shared pair. Basically, the oxygen atom, instead of hogging that pair of electrons to itself, it can share it with the nitrogen and turn it into a bond. And specifically what happens is you form a double bond. So now the nitrogen has 2 single bonds to 2 different oxygen atoms, and then it has 1 double bond to that single oxygen atom. And so what that ends up with is it now has 4 total pairs of electrons that it's sharing, giving it that octet of 8 electrons, right? Now the nitrogen has stepped up and gotten those 8 electrons that it wanted, right, for its full octet. So this is basically in the last example with the PCl3, after you assigned the lone pairs, you had extra electrons so that you could put a lone pair on the central atom. Here, after assigning our outer atom lone pairs, we didn't have any electrons left, but we did not have an octet on the central atom. So that's where we form double bonds, triple bonds if you need them. That's where you start to form those bonds where you pull things in, forming those secondary bonds, converting the lone pair. And importantly, that lone pair counted for oxygen. Since it's still a bond for oxygen, that oxygen atom hasn't lost its octet. So you can always do this process. You always start with putting lone pairs on the outside and then turn them into double bonds if you need them. Okay, now oxygen still has 8. Okay, looking for any more questions on participation 625. We are over halfway through this set of videos. See you in the next one.